Welcome to the second part of lecture 17, the Laplacian in spherical coordinates. We're still going to be differentiating and collecting all those terms. Let's start with a focus on what the spherical coordinates are. On the left here I have a plot of a sphere showing r. There are also two angles, theta and phi. Theta is the angle r makes with the z-axis, and phi is the angle that the projection of r onto the xy plane makes with the x-axis. So as I rotate around the x-axis, phi will increase, and as I rotate down from the z-axis, theta will increase. What is pictured on the plot for you are the unit vectors er, e theta, and e phi. Er is a unit vector in the r direction. E theta is a vector that is perpendicular to ER but lies in the plane given by the z-axis and the projection of r into the xy plane. And E phi is the unit vector that is perpendicular to ER and E theta. And then those three vectors make the triad that is the local triad for the coordinate system. So let's try and work out exactly what those unit vectors are. ER is in the radial direction, so it's going to be x times the unit vector in the x direction plus y times the unit vector in the y direction plus z times the unit vector in the z direction, all divided by r. When I work that out in the spherical coordinates, it becomes sine theta cos theta I hat plus sine theta sine phi j hat plus cos theta k hat. And now I have to construct E theta. The key thing to remember is the I hat j hat component is the component that is lying, that's the projection of r onto the plane, the xy plane, and I want to keep the relative proportion of the x component to the y component the same. Then I'll be lying in this plane that is given by z and the projection of r onto the xy plane. And if you look at that, you can see there's a sine theta that's multiplying something in the xy plane multiplied by cos theta multiplying something in the z-axis. And so how do I find something perpendicular? If one of them is sine theta cos theta, the other one should be cos theta minus sine theta. So you see E theta is constructed by cos theta cos phi I hat plus cos theta sine phi j hat minus sine theta k hat. And you can verify that that is a vector that lies in that particular plane. It's oriented in that particular direction. The only thing that's uncertain is whether or not I multiply it by a plus or minus 1. And now to calculate E phi, I take the cross product of these two. Or I can play the same trick by looking just at the xy plane and finding the vector perpendicular to cos phi I hat plus sine phi j hat, which I can just tell you is going to be sine phi I hat minus cos phi j hat, and then I can multiply that by plus or minus 1. And indeed the answer is you multiply by minus 1, and you get that E phi is minus sine phi I hat plus cos phi j hat. Okay, we've got our unit vectors. We can very easily see these unit vectors don't depend at all on r. As r gets bigger, the unit vectors don't change the direction, but they obviously depend on both theta and phi, so I have a couple of derivatives I have to work out. Let's look at the derivative of ER with respect to theta. You see there's a sine theta times the first two terms and a cos theta times the last term. The sine theta will go to cos theta, the cos theta will go to minus sine theta, and lo and behold, that is actually equal to E theta. So the derivative of ER with respect to theta is E theta. The derivative of ER with respect to phi, I'm going to get my cosine phi goes to minus sine phi, and my sine phi goes to cosine phi, and you can see that's equal to sine theta times E phi. And so I get my second derivative there. When I look at the derivative of E theta with respect to theta, the cosine theta term will go to minus sine theta, the sine theta will go to cosine theta, but you see that that whole thing is going to go to minus ER. And so that's what that derivative is. When I take the derivative with respect to phi, I'm going to have a cosine phi go to minus sine phi and a sine phi go to cosine phi. And indeed, you see it's going to just be cosine theta times E phi. And so now I only have to work out the derivatives of E phi with respect to theta and with respect to phi. Well, E phi has no theta dependence, so the derivative with respect to theta of that is equal to 0. Whereas E phi does have phi dependence, and you can see when I take the derivative, I'll get minus cosine phi minus sine phi times I hat minus sine phi times j hat. And now I have to write that as a linear combination of ER and E theta, and it doesn't take too much to recognize it's going to be minus sine theta ER minus cos theta E theta, because then I'll get a minus sine squared theta and a minus cos squared theta for the I hat and the j hat components, and the k hat components are going to cancel. And so you should be able to verify that indeed that is going to be the derivative of E phi with respect to phi. All right, we've got these derivatives worked out. Now we're going to use our easy method to find out what the gradient is. We're going to look at the change in f as r, theta, or phi changes. That is just determined by the partial derivatives with respect to r, theta, or phi multiplied by the respective delta r, delta theta, or delta phi. And we want to also calculate how does the position vector change as r, theta, or phi changes. Well, in the r hat direction, or the ER direction, it changes by delta r. The change in the theta direction is going to be r times delta theta, because I'm pivoting on a circle that has a radius r, and the distance in the phi direction is going to be r sine theta delta phi, because the radius of that circle is projected onto the xy plane, so it becomes r sine theta. And we now have to write delta f as delta s dotted into the gradient of f. And as we did before, what that ends up being is we get the partial derivatives with respect to r, theta, or phi, and we have to divide by the factors in delta s that are not delta r, delta theta, or delta phi. So for the r, that factor is 1. For the theta, it'll be 1 over r. For the phi, it'll be 1 over r sine theta. And so I can put that together and get the gradient is er d by dr plus e theta 1 over r d by d theta plus e phi 1 over r sine theta d by d phi. All right, I've got the gradient. I'm going to copy the derivatives of the unit vectors above because we're going to need that. And now we're going to go through the same process we did before to calculate the Laplacian. We're going to look at the gradient dotted into itself, taking into account the fact that the derivatives can act on the unit vectors. And we look at d by dr. d by dr does not affect any of the unit vectors because none of the unit vectors depend on r. And so the er dot er is going to guarantee that that's going to become a d squared by dr squared. When I look at the e theta, the d by d theta will affect er, e theta, and e phi. It also will have a term that just goes straight through with the e theta term. And since the derivative of e theta is perpendicular to e theta, that term will, when it's dotted into e theta, is going to give 0. And so I'm going to get a term for the derivative of er with respect to theta. I'll get a term with the derivative of e phi with respect to theta, but remember e phi doesn't depend on theta, so that derivative is 0. And then I'll get a term that has a second derivative with respect to theta that's coming from the e theta dot e theta. When I look at the e phi, I'm going to have a derivative of er with respect to phi. I'm going to have a derivative of e theta with respect to phi. And then I'll have the second derivative with respect to phi because the derivative of e phi with respect to phi is perpendicular to e phi. And I'm taking a dot product with e phi. Okay, so that's a lot of words. Let's take a look at what it looks like. So I get this d squared by dr squared that we talked about before. Then I have this term with the d by d theta acts on the er. And then I have the term where I have the second derivative with respect to theta. Then I have the term where the d by d phi acts on er. I have the term where the d by d phi acts on e theta. And finally, I have the second derivative with respect to phi squared term as well. So now we have to go and look up what they are. So d by d theta of er, that's just equal to e theta. And then e theta dot e theta is equal to 1. So that second term becomes 1 over r d by dr. The third term, when I look at d by d phi of er, d by d phi of er is just sine theta times e phi. So when I take the dot product with e phi, I get a sine theta. Well, that cancels the sine theta in the denominator, and I get, once again, 1 over r d by dr. When I look at the fifth term, I have a d by d phi of e theta. Well, d by d phi of e theta is cosine theta e phi. So e phi dot e phi will give 1, but now I get a cosine theta divided by a sine theta in that expression. And then I have the final term that's the second derivative with respect to phi. So let's write all of those terms down. I get this 1 over r d by dr. I get a second 1 over r d by dr. I get this cosine theta over r squared sine theta d by d theta. And then I have the other terms are all the second derivative terms, the ones that I would have just immediately written down after looking at what the gradient was. Okay, it turns out we can simplify these by doing some derivatives that we put together. So d squared by dr squared plus 2 over r d by dr can be written as 1 over r squared d by dr of r squared d by dr. The two terms that have derivatives with respect to theta can be written as 1 over r squared 1 over sine theta d by d theta of sine theta d by d theta. And then I have the last term, which involves the second derivative with respect to phi squared, which I don't touch. All right, we've gotten the Laplacian now in spherical coordinates. We want to look at some other ways in which we can calculate it. As you remember, if we had the divergence, we can then substitute in for the vector field with the gradient, and then we had an alternative way of calculating the Laplacian. So I'm not going to derive for you what the divergence is in spherical coordinates. This can be done by using the techniques that were discussed in the textbook, where we do these integrals over the small region of the surface area and of the volume in spherical coordinates. And what you find is you get this expression that's written for you here. The divergence of f is 1 over r squared d by dr of r squared, the component of f in the radial direction, plus 1 over r, 1 over sine theta d by d theta of sine theta times the component of f in the e theta direction, plus 1 over r sine theta, the derivative of f in the e phi direction with respect to phi. Well, we're going to substitute in f equals gradient of f, where the gradient is this expression that we already got in spherical coordinates. And when we do that, you see the first term will have inside the parenthesis r squared d little f dr. The second term will have a sine theta times a 1 over r d little f by d theta. And the third term will have a 1 over r sine theta times a 1 over r sine theta d squared f d phi squared. And so as we put that all together, we get these three terms, one involving derivatives with respect to r, one involving derivatives with respect to theta, and one involving derivatives with respect to phi. And you see that that exactly agrees with the result that we wrote at the top of the page. And so this is just verifying that things are actually working out. And what I hope I've been able to convince you with this is that it is possible to calculate these different objects, gradient, divergence, or Laplacian, in these complicated coordinate systems. It requires care and persistence to get the right result because there's lots of terms. And the reason why we have lots of terms is because the unit vectors are actually changing as the different variables change. And so I have to take into account the derivatives of how the unit vectors change with respect to the particular variables that are changing, and that really complicates the calculation. But if you keep your wits about you and you proceed slowly and carefully, you're able to get through it and do this. And I should note that it's very important that everyone has seen these kinds of formulas. I'll never ask you to derive one of these on a test, but I do expect you to be able to be familiar with them and be able to use them and understand them, and in particular understand how we got them, because that's really the important thing.